Welcome to Softly Curious. Tonight we begin with something almost invisible in its simplicity, a gap in the land. A narrow stream cutting through soil, a shallow ravine interrupting a path, a river widening just enough to stop movement. Long before calculations, before drawings, before engineering became a discipline, there was only this quiet obstacle and the need to move beyond it. The earliest bridges were not designed in the way we understand design today. They were discovered. A fallen tree across water was not an invention but an observation. A flat slab of stone lodged naturally between two banks was not constructed but noticed. Early humans learned quickly which surfaces could bear weight and which would shift beneath their feet. Stone proved reliable because it resists compression, the force that pushes material inward and squeezes it tighter. Without formal language for physics, people understood through repetition that a rock that did not crack under pressure could be trusted again. Stability was learned through survival. Over time, chance gave way to intention. Logs were placed deliberately across narrower crossings. Branches were layered to distribute weight more evenly. Earth and smaller stones were packed into gaps to create continuity underfoot. These early wooden bridges were rarely permanent, yet they carried a crucial realization. A gap in the landscape did not have to dictate direction. It could be negotiated, shaped, and gradually controlled. Wood introduced flexibility into the story of bridges. Unlike stone, it bends before it breaks. Under compression, its fibers shorten. Under tension, they stretch. This dual behavior allowed early builders to span distances that a single rock could not manage alone. But wood also absorbs moisture, decays over time, and weakens from within. The majority of early timber bridges have vanished, not because they were poorly conceived, but because their material was temporary by nature. They performed their function and quietly returned to the ground. Stone, in contrast, holds its shape across centuries. As communities settled and trade routes solidified, bridges evolved from temporary crossings into lasting infrastructure. A bridge was no longer a convenience. It became a statement of permanence. Markets depended on reliable passage. Armies required consistent routes. Cities expanded along rivers, and crossing points became strategic anchors within urban growth. It is in this context that the arch emerges as one of humanity's most important structural discoveries. Rather than resisting gravity with a straight beam that fights against downward force, an arch redirects weight sideways. Compression travels along its curve and disperses into the supports at each end. Each stone presses into its neighbor, and the structure strengthens under appropriate load. Within limits, added weight increases stability because it deepens the compressive bond between the elements. At the center of a true stone arch sits the keystone, the final block placed at the highest point. Its importance lies not in size or decoration, but in timing. Once inserted, it locks the surrounding stones into a single structural system. Remove it, and the arch loses coherence. Leave it in place, and each stone depends on the next in a continuous loop of shared pressure. The arch is not a collection of stones. It is a collective agreement between them. Stone excels in compression, but performs poorly in tension, the force that pulls material apart. The brilliance of the arch is that it keeps the stone almost entirely in compression. Granite, limestone, and basalt can withstand enormous compressive loads, often far exceeding the demands placed upon them in bridge construction. By shaping the path of force into a curve, early builders ensured that gravity would help stabilize the structure rather than tear it apart. One of the oldest surviving examples of this principle can still be found in Greece at the Art Deco Bridge. Constructed during the Mycenaean period more than 3,000 years ago, it remains in place and occasionally in use. Its stones were carefully arranged without mortar, shaped and positioned so that each block leans into the next. The bridge is modest in scale, yet it has endured seismic activity, seasonal floods, and the slow erosion of time. Its survival is not an accident of luck, but a consequence of structural clarity. Centuries later, Roman engineers refined the arch into a repeatable system. They standardized proportions, improved stone cutting techniques, and incorporated early forms of concrete to enhance durability. Rivers that once defined the limits of expansion could now be crossed with confidence. Bridges became durable arteries within growing empires, allowing goods, information, and people to move with increasing efficiency. In Rome itself, the Pons Fabricius has stood since 62 BCE, connecting the banks of the Tiber for more than 2,000 years. Though it has been repaired and maintained, its fundamental structure remains intact. People continue to walk across the same arches that ancient citizens once used. Compression still flows through its curve, transferring load into the riverbanks just as intended. From the Roman era alone, historians estimate that approximately 300 stone bridges survive today in some recognizable form. Some remain fully operational, while others stand partially intact as historical remnants. When considering the scale of Roman infrastructure, this number is strikingly small. Thousands of bridges were constructed across the ancient world, yet only a fraction endure. Across all of antiquity, the total number of bridges that have survived into the present likely does not exceed a few hundred. Floods undermined foundations. Wars targeted crossings for strategic disruption. Stones were repurposed for new buildings. Maintenance lapsed as cities shifted or declined. The survival of any bridge across millennia required not only sound design, but also ongoing human care. When we step back and look at the timeline, the perspective becomes clear. Humans have been building bridges for thousands of years, yet only a few hundred ancient examples remain. The vast majority have disappeared, leaving only traces in soil or historical records. What survives does so because geometry aligned with material strength and because generations maintained what they inherited. A bridge may appear to be a simple connection between 2 points, but structurally it is an ongoing negotiation with gravity. It accepts downward force and guides it along a controlled path into the earth. Thousands of years ago, someone placed stones in a curve and discovered that they would hold each other in balance. Today, a small number of those early decisions still stand, quiet witnesses to the long history of crossing. As rivers widened and valleys deepened, the arch began to meet its limits. Stone could only travel so far before its own weight became a problem. The longer the span, the heavier the structure needed to be, and the heavier it became, the more force it had to carry. At a certain point, adding more material no longer solved the problem. It amplified it. This is where bridges change direction, not outward, but upward. Instead of fighting gravity with mass, engineers began to cooperate with it using tension. Tension is the force that pulls material apart. Unlike stone, which thrives under compression, materials like iron and steel perform exceptionally well when stretched. When properly designed, a cable becomes stronger as it carries load because the internal forces align along its length. In a suspension bridge, the roadway does not push downward into solid arches. It hangs. The weight of the deck is transferred vertically into cables, and those cables curve naturally between 2 high towers. This change in logic transformed what a bridge could be. Instead of compressing material into the ground through thick supports, suspension systems stretch material across space and anchor it at the ends. The entire structure becomes an exercise in balance between downward force and outward pull. The anchor blocks at each end of a suspension bridge are often hidden from view, yet they are among the most critical elements in the system. These massive concrete or stone foundations resist the horizontal pull of the main cables. When vehicles move across the deck, the load travels upward through vertical suspenders into the main cable, then outward toward the anchors. Without sufficient anchorage, the entire structure would draw inward under tension. In this configuration, The towers serve primarily as compression members. They hold the cables high above the water or ground, transferring vertical forces into their foundations. The cables carry tension. The towers carry compression. The anchors resist horizontal pull. Each component performs a distinct role within a coordinated system. As spans grew longer, another concept became central: the main span. The main span refers to the longest uninterrupted distance between two primary supports, typically the towers in a suspension bridge. It is not the total length of the bridge, which may include approach sections and additional spans. The main span is the structural heart of the system, the point where forces are most dramatically expressed. For centuries, engineers gradually extended this distance. Longer spans required stronger cables, taller towers, and deeper foundations. Steel made these expansions possible. Compared to earlier materials, steel offers high tensile strength, meaning it can withstand significant pulling forces without permanent deformation. One of the most iconic examples of suspension design is the Golden Gate Bridge. When it opened in 1937, its main span was the longest in the world. The bridge stretches across a strait known for strong currents and unpredictable winds. Its cables contain thousands of individual steel wires bundled together, distributing tension across countless strands. The visual lightness of the structure contrasts with the immense forces flowing through it. Yet as spans lengthened, engineers discovered that length introduces a new challenge: movement. Suspension bridges are flexible by design. This flexibility allows them to absorb wind and dynamic loads, but it also introduces the possibility of oscillation. When external forces match a bridge's natural frequency, a phenomenon called resonance can occur. Resonance happens when repeated forces align with the structure's inherent vibration pattern, amplifying motion rather than dampening it. Wind, in particular, can interact with long spans in complex ways. Air flowing across a deck can create lift or twisting forces. If these forces reinforce the bridge's natural oscillations, motion can grow progressively stronger. Modern suspension bridges undergo extensive aerodynamic testing in wind tunnels to ensure that their shapes reduce the risk of unstable vibration. Subtle changes in deck profile, stiffening trusses, and cable arrangement can significantly alter airflow behavior. Today, the record for the longest main span belongs to the Akashi-Kekkyo Bridge. Its central span measures 1,991 meters, extending nearly 2 kilometers without intermediate support. The bridge crosses a seismically active strait in Japan, requiring not only tensile strength, but also resilience against earthquakes and typhoons. During its construction, an earthquake shifted one of its towers slightly, increasing the planned span length by nearly a meter. The design absorbed this change without structural compromise. The distinction between total bridge length and main span length often causes confusion. A bridge may extend for many kilometers due to approach sections over land or shallow water, yet its main span could be comparatively modest. The main span represents the longest single leap over open space. It is the measure of structural daring rather than geographic coverage. As spans increase, the weight of the cables themselves becomes significant. In very long suspension bridges, a substantial portion of the cable tension arises not from traffic, but from the cable's own mass. Engineers must account for this self-weight when determining cable diameter and anchor capacity. Every additional meter adds force that must be balanced. Temperature also plays a role. Steel expands in heat and contracts in cold. Over large distances, thermal expansion can shift the position of the deck by noticeable margins. Expansion joints allow movement without inducing excessive stress. What appears rigid from afar is, in reality, a controlled system of movement. In suspension design, elegance and complexity exist together. The roadway may appear to float, yet it is secured to the earth through massive anchor blocks at either end. The curve of the main cable is not decoration, but the visible trace of tension distributed along its length. Unlike stone arches that rely on compression pressing inward, suspension bridges depend on steel pulling outward. This shift from compression-dominant to tension-dominant systems marks a fundamental change in structural thinking, where weight is carried through controlled stretching rather than mass. As the main span increases, sensitivity increases with it. Longer bridges move more and demand careful control of wind and dynamic forces. Aerodynamic stability becomes essential, and anchors must resist immense horizontal loads from the cables. Extending a span is less about breaking records and more about refining how forces travel through the structure. Gravity is guided upward into cables, outward toward anchors, and down into the ground. And the bridge stands because every force follows a deliberate path. Stone carried bridges across centuries, but it carried limits with it. Its strength under compression made arches possible, yet its weight restricted how far a structure could reach. As trade expanded and industry accelerated in the 18th century, new materials began to alter the scale of ambition. The change did not happen suddenly. It emerged from furnaces, workshops, and experiments in metallurgy that gradually reshaped how force could be managed. Iron was the first decisive shift. Unlike stone, iron could be cast into shapes. Dikme de mir, or cast iron, is produced by pouring molten iron into molds. Once cooled, it becomes hard and strong under compression, but brittle under tension. It does not bend much before breaking. This brittleness limited its reliability in certain structural roles, yet it offered something revolutionary: repeatability. Components could be manufactured in controlled forms rather than carved individually from stone. In 1779, the iron bridge opened across the River Severn in England. It was the first major bridge constructed primarily of cast iron. Its form resembled earlier stone arches, but the material signaled a new era. Iron allowed thinner structural elements, reducing weight while maintaining compressive capacity. The bridge was both experimental and symbolic, standing at the beginning of the Industrial Revolution. Cast iron's weakness under tension soon became apparent. While it could resist being squeezed, it fractured more easily when stretched or bent. This limitation encouraged further refinement. Engineers began to seek materials that combined strength in both compression and tension. The answer was steel. Steel is essentially iron with controlled amounts of carbon and other elements, carefully processed to improve its mechanical properties. Compared to cast iron, steel is far more ductile. Ductility means the material can deform under stress without sudden failure. Instead of snapping abruptly, it bends and redistributes force. This property made steel ideal for bridges that needed to handle dynamic loads such as moving trains and heavy vehicles. With steel came new structural forms, and one of the most influential was the truss. A truss is a framework composed of interconnected elements arranged in triangular patterns. The triangle is structurally rigid because its shape cannot change without altering the length of one of its sides. In a square, joints can rotate and distort into a parallelogram. In a triangle, geometry resists deformation naturally. This geometric rigidity allowed trusses to distribute loads efficiently. Instead of relying on thick, solid beams, engineers could use slender steel members arranged in repeating triangular units. Each element carried either tension or compression, and together they formed a stable network. Weight was reduced without sacrificing strength. Truss bridges spread rapidly during the 19th century, particularly in regions undergoing railway expansion. Steel members could be prefabricated, transported, and assembled on site. The repetition of triangular modules simplified both design and construction. Load paths became visible in the lattice of metal, each diagonal brace playing a defined role. Connections were as important as members. In early steel bridges, rivets were the dominant method of joining components. A rivet is a metal pin inserted through aligned holes in structural members and then deformed at the end to lock it in place. When heated and hammered, rivets expanded to fill gaps tightly. Thousands, sometimes millions, of rivets held large bridges together. Each one transferred force between elements, creating continuity across the structure. Riveted construction required precision and labor. Teams worked in coordinated sequences, heating rivets until they glowed, inserting them quickly before cooling, and hammering them into secure heads. The process was noisy and intense, yet it produced remarkably durable joints. Many 19th century riveted bridges remain functional today, evidence of both material strength and craftsmanship. Steel also introduced new considerations. Unlike stone, metal responds noticeably to temperature. Isalgenlesme, or thermal expansion, refers to the tendency of materials to expand when heated and contract when cooled. Over long spans, even small temperature changes can produce measurable movement. Engineers began incorporating expansion joints and roller bearings to allow controlled motion. Without these accommodations, thermal stress could accumulate and distort the structure. One of the most striking examples of large-scale steel construction is the Forth Bridge, completed in 1890. Spanning the Firth of Forth in Scotland, it remains one of the world's great cantilever railway bridges. Its massive steel trusses extend outward from piers, balancing loads through tension and compression in opposing arms. The visual complexity of the structure reflects the internal choreography of forces flowing through its members. The Forth Bridge demonstrated that steel could achieve spans and load capacities beyond the practical reach of stone or cast iron. Trains, heavier than typical road traffic, required structures capable of handling concentrated loads and vibration. Steel's combination of tensile strength and ductility made this possible. The bridge became not only a transportation link, but a declaration of industrial capability. As iron gave way to steel, bridges became lighter relative to their span. Material efficiency improved. Instead of relying on mass, designers relied on geometry and metallurgical precision. This shift mirrored broader industrial trends. Standardization replaced hand carving. Manufacturing complemented masonry. Infrastructure began to reflect factory logic. The transition from cast iron to steel was not merely technical. It altered how engineers thought about possibility. When material properties expand, imagination follows. Longer spans, heavier loads, and faster transport networks became achievable because steel offered reliable performance under both tension and compression. In this period, the language of bridges changed. Instead of describing only arches and piers, engineers spoke of stress distribution, load paths, and fatigue. Fatigue refers to the weakening of a material under repeated loading cycles. Steel can endure millions of cycles, but only within defined limits. Understanding these limits required new analytical methods and careful testing. The industrial turning point in bridge construction was therefore more than a material upgrade. It was a conceptual evolution. Structures became assemblies of calculated components rather than monolithic masses. Triangles replaced thick stone blocks. Rivets stitched members into unified systems. Temperature became a design variable rather than a surprise. Iron opened the door. Steel expanded the horizon. By the end of the 19th century, bridges no longer relied primarily on the compressive strength of stone. They leveraged tensile capacity, geometric rigidity, and industrial production. The shift from cast iron to steel reshaped the skyline of cities and the connectivity of nations. Material science had entered the conversation, and with it came a new understanding. The limits of a bridge are often the limits of its material. Steel transformed bridges in the 19th century, but the 20th century introduced a material that would quietly dominate the landscape: concrete. At first glance, concrete appears simple, a mixture of cement, water, sand, and aggregate. Yet once it hardens, it becomes stone made to order, shaped not by geology, but by intention. Unlike carved blocks, concrete can be poured into molds, forming curves, slabs, and piers in almost any geometry required. Concrete performs exceptionally well under compression, much like natural stone. It resists being squeezed with remarkable efficiency, which makes it ideal for columns, piers, and deck slabs. However, like stone, plain concrete is weak under tension. If pulled or bent excessively, it cracks. The solution to this limitation was reinforcement. Reinforced concrete combines concrete with embedded steel bars, known as rebar, placed strategically within the structure. The concrete carries compressive forces, while the steel absorbs tension, creating a composite system stronger than either material alone. This pairing changed the scale of possibility. Instead of relying solely on visible steel frameworks, engineers could hide tensile strength inside solid forms. Bridges could appear heavier and more grounded while internally managing complex stress patterns. Reinforced concrete also offered durability and resistance to weathering when properly protected, making it suitable for highways, urban overpasses, and large viaducts. As spans and traffic demands increased, engineers sought even greater efficiency. This led to pre-stressed concrete, a technique in which steel tendons are tensioned before or after the concrete cures. In pre-tensioned systems, steel is stretched first and concrete is cast around it. Once the concrete hardens and the tension is released, compressive force is introduced into the structure. In post-tension systems, ducts are formed within the concrete and steel cables are tightened afterward. In both cases, the concrete is placed in a state of compression before carrying service loads, reducing cracking under tension. Pre-stressing allowed longer spans with thinner sections. Instead of reacting to tension after it occurred, engineers anticipated it and counteracted it in advance. The structure begins its life slightly compressed, so everyday loads merely reduce that compression rather than pulling the material apart. This method extended bridge spans without dramatically increasing weight, contributing to the growth of elevated highways and multi-lane viaduct systems across the world. Construction methods evolved alongside material science. Segmental construction became common for long concrete bridges. Rather than pouring an entire span at once, engineers fabricate individual segments, often in controlled factory environments, and then assemble them on site. Each segment is carefully aligned and connected, typically using post-tensioned cables that run through multiple sections. This approach improves quality control and accelerates construction, especially over water or difficult terrain. Segmental methods also support incremental launching, where sections of a bridge are pushed outward from one side in stages. The structure extends gradually across a gap without the need for extensive temporary scaffolding below. This technique reduces environmental impact and allows bridges to cross wide valleys or rivers with minimal disruption. It reflects a modern preference for precision and efficiency over brute mass. Beyond traditional reinforcement, newer materials have entered the field. Fiber-reinforced polymers, for example, incorporate glass or carbon fibers within resin matrices to produce lightweight components with high tensile, strength, and corrosion resistance. Search for materials that combine strength, flexibility, and longevity. While not yet replacing steel on a large scale, these composites are used in specific applications where reduced weight and long-term durability are priorities. They represent an ongoing. As materials improved, the ambition of scale expanded dramatically. Bridges were no longer limited to singular spans across prominent rivers. Entire transportation corridors could be elevated for kilometers at a time. In this context, a distinction becomes important: the difference between main span length and total bridge length. The main span measures the longest uninterrupted distance between major supports. Total length, by contrast, includes all sections of the structure, including approach viaducts and repetitive spans over land or shallow water. The longest total bridge in the world today is the Danyan Kunshan Grand Bridge. Stretching approximately 164 kilometers, it forms part of a high-speed railway line in China. Its scale is not defined by a single dramatic leap across open water, but by sustained extension across varied terrain, including rice paddies, canals, and lakes. The structure consists largely of repeated concrete spans supported by piers, demonstrating how modern materials and standardized construction can achieve extraordinary cumulative length. The record held by this bridge illustrates how modern engineering measures achievement differently. It is not always the single longest main span that defines scale, but the ability to maintain structural continuity across vast distances. Reinforced and pre-stressed concrete make this possible through durability, cost efficiency, and adaptability to repetitive forms. The material supports not only isolated landmarks, but entire infrastructural networks. Concrete, once perceived as heavy and inert, has become a versatile medium for shaping space. Through reinforcement, pre-stressing, and segmental assembly, it allows bridges to stretch far beyond what earlier generations imagined practical. The longest bridge on Earth does not rely on a single daring leap. It relies on disciplined repetition, material refinement, and the quiet strength of compression guided by steel hidden within. A bridge may appear to float above water, but its true story begins below the surface. What we see, towers and decks and cables, depends entirely on what we do not see. Beneath rivers and tidal currents lies the quiet negotiation between structure and earth. Before a single span can rise, the ground must agree to carry it. Water complicates everything. A riverbed is rarely solid rock. It is often composed of layered sediments, sand, silt, gravel, clay. These materials shift, they compress, they erode. When engineers speak of scour, they refer to the gradual removal of sediment around a foundation caused by flowing water. Scour is not dramatic. It does not announce itself with noise. It works patiently, carrying grains downstream, lowering the riverbed millimeter by millimeter until a once buried foundation becomes exposed. If enough material is removed, the support loses stability. A pier designed to transfer load safely into the ground may suddenly find part of that ground missing. Bridges have failed not because their superstructures were weak, but because the river quietly reshaped the terrain beneath them. To resist scour, foundations must reach deeper than the visible riverbed. Engineers seek bedrock, the solid layer of stone beneath loose sediments. Bedrock offers predictability. It does not shift with seasonal currents. It does not compress significantly under load. When a bridge foundation reaches bedrock, the structure gains a reliable anchor point against gravity and flow. Reaching that layer, however, is rarely simple. In deep or fast-moving water, traditional excavation methods are impractical. This is where the caisson enters the story. A caisson is a large watertight chamber used to create dry working conditions underwater. It is typically constructed on land, floated into position, and then carefully lowered to the riverbed. Once in place, workers excavate sediment from within, allowing the caisson to sink gradually under its own weight. As material is removed from inside, the chamber descends until it reaches stable ground or bedrock. Concrete is then poured into the hollow space, forming a massive permanent foundation. The caisson itself becomes part of this substructure, buried beneath the waterline, invisible but essential. Working inside a caisson can be dangerous. When foundations must extend deep below the river surface, compressed air is used to keep water from flooding the chamber. Air pressure inside the caisson is increased to counteract the surrounding water pressure, creating a dry environment where workers can dig. This artificial atmosphere, however, places strain on the human body. Under high pressure, gases dissolve more readily into the bloodstream. When workers return to normal surface pressure too quickly, dissolved gases form bubbles within tissues and blood vessels. This condition, known as decompression sickness, can cause joint pain, neurological damage, or even death. It was once referred to as caisson disease, a reminder that building foundations required not only engineering precision, but physical endurance. One of the most famous examples of underwater foundation work can be found in the construction of the Brooklyn Bridge. Completed in 1883, the bridge required enormous stone towers anchored deep into the East River. Massive timber caissons were sunk to the riverbed and gradually lowered as workers excavated beneath them. Compressed air kept the water out, but many laborers suffered from decompression sickness. At the time, the condition was poorly understood, and its risks were discovered through experience, rather than prior medical knowledge. The caissons for the Brooklyn Bridge descended to depths of more than 20 meters below the waterline. Before reaching stable strata, the process was slow and physically demanding. Fires occasionally broke out inside the pressurized chambers due to flammable gases and limited ventilation. Despite these challenges, the foundations were completed, and they continue to support the bridge today. This example illustrates an essential principle. The visible elegance of a bridge depends on unseen mass below. Towers may rise gracefully above water, but their stability originates in foundations that outweigh them many times over. In some cases, the foundation volume is comparable to a small building, hidden entirely beneath the river. Water also exerts pressure in subtle ways. Hydrostatic pressure increases with depth, meaning the deeper a foundation extends, the greater the force exerted by surrounding water. Structural components must resist not only vertical loads from above, but lateral pressure from all sides. Design calculations must account for buoyancy as well, since large submerged structures experience upward force from displaced water. Sediment conditions vary dramatically from one site to another. A river delta may contain soft clay extending dozens of meters before reaching bedrock. In such cases, engineers may use deep piles, long columns driven or drilled into the ground to transfer load through weak layers into stronger strata below. These piles act like roots, extending downward until sufficient friction or bearing capacity is achieved. The interaction between foundation and soil is studied in geotechnical engineering, a field concerned with how earth materials behave under load. Soil is not uniform. It consolidates over time. It responds differently to static and dynamic forces. A bridge foundation must account for long-term settlement, ensuring that uneven sinking does not distort the superstructure above. Building against nature means acknowledging that water and soil are active participants in the system. Rivers flood, currents accelerate, sediment migrates. Foundations must anticipate these movements rather than assume stillness. Protective measures such as riprap, large stones placed around piers, help reduce scour by stabilizing the surrounding bed. In many ways, the foundation phase of bridge construction is the least visible yet most decisive. Mistakes made above water can often be repaired. Mistakes below are far more difficult to correct. Once piers and towers rise, access to deep foundations becomes limited. Precision at the beginning ensures stability for decades or centuries. The story of underwater foundations is not dramatic in appearance. There are no sweeping spans or dramatic silhouettes. Instead, there is excavation in darkness, careful measurement of sediment layers, and slow descent toward bedrock. It is an engineering conversation with geology, conducted quietly and often unseen. When crossing a bridge over water, it is easy to focus on the view, the horizon, the open space. Yet below the surface lies a different structure, one shaped by pressure, erosion, and depth. The bridge stands not only because of what rises above the river, but because of what settles into it. In the end, building against nature does not mean defeating it. It means understanding its forces deeply enough to work within them. Foundations anchored in bedrock, protected against scour, and designed to withstand pressure allow the visible structure to remain calm above. Beneath the waterline, gravity and geology meet steel and concrete in a quiet agreement that makes every crossing possible. When bridges rise higher, they leave the predictable resistance of ground and water and enter a different environment altogether. At elevation, wind becomes a structural partner, sometimes gentle, sometimes insistent. Gravity still pulls downward, but air begins to push sideways. The higher a structure climbs, the more it must negotiate with forces that cannot be seen but are constantly present. One response to height is the cable-stayed system. Unlike suspension bridges, where cables curve between two distant anchor points, cable-stayed bridges connect the deck directly to towers using straight, radiating cables. Each cable runs diagonally from the tower to a specific point on the roadway. The load travels through these cables into the tower, which transfers compression into the ground. The system is efficient because it reduces the need for massive anchor blocks and allows for relatively stiff deck behavior. In a cable-stayed bridge, the towers are not merely supports, but central structural actors. They carry immense compressive forces while balancing tension from dozens of cables pulling in multiple directions. Stability depends on precise geometry. If one cable carries slightly more load than intended, the distribution across the system shifts. Engineers calculate these forces carefully to maintain equilibrium under traffic, temperature changes, and wind. Wind, however, introduces complexity that goes beyond static load. Air moving across a bridge deck creates pressure differences. These pressures can induce vibration. When wind interacts with a structure's natural frequency, a phenomenon known as aeroelastic flutter can occur. Aeroelastic flutter is a dynamic instability where aerodynamic forces and structural motion reinforce each other, amplifying oscillation rather than dampening it. The structure begins to move in a self-sustaining pattern driven by airflow. Flutter is not simply strong wind. It is resonance shaped by aerodynamics. Even moderate winds can produce large oscillations if conditions align. Modern bridge design treats this possibility with caution. Engineers do not assume that strength alone will prevent instability. They study how wind flows around and beneath the deck, how it interacts with edges, and how slight modifications in shape can alter behavior dramatically. Wind tunnel testing has therefore become a standard part of long-span bridge design. Scale models are placed in controlled airflow environments where velocity, angle, and turbulence can be adjusted. Sensors measure lift, drag, and oscillation patterns. Through these experiments, engineers observe how a bridge might respond before it is built. Adjustments to deck profile, cable arrangement, or stiffening elements can be made early, reducing risk later. Height intensifies these concerns. Tall towers behave differently from shorter supports. As elevation increases, exposure to stronger and more consistent wind grows. Slender forms are visually elegant, yet they must resist bending and buckling. Engineers analyze tower stability using principles of structural mechanics, ensuring that compressive forces do not exceed critical thresholds that could lead to instability. The Millau Viaduct offers a compelling example of height managed with precision. Its tallest mast rises higher than the Eiffel Tower, yet the structure appears remarkably light against the landscape. The bridge spans a deep valley, supported by slender concrete piers and steel masts that anchor a cable-stayed deck. Wind conditions in the region required extensive aerodynamic study before construction began. Despite its height, the viaduct maintains stability through careful proportion and material coordination. The deck is streamlined to reduce turbulent flow. Cables are arranged symmetrically to balance forces. Foundations anchor the piers securely into the valley floor, ensuring that lateral forces do not accumulate unchecked. The result is a structure that feels delicate, yet is rigorously engineered. As bridges climb higher and spans grow longer, structural risk shifts from simple load-bearing to dynamic performance. Engineers must anticipate not only how much weight a bridge can carry, but how it moves. Flexibility is no longer a secondary trait, but a defining characteristic. Movement must be allowed within safe limits, and vibration must be controlled without over-stiffening the system. In elevated bridges, stability is a conversation between mass, tension, compression, and airflow. The structure cannot ignore the wind. It must shape itself around it. Height invites exposure, and exposure demands understanding. A bridge that rises above the landscape does not conquer the air. It learns how to move within it, holding steady not through rigidity alone, but through balance. A bridge does more than carry weight. It carries movement, and movement carries value. Once a crossing becomes reliable, it begins to shape the life around it. Roads adjust their paths toward it. Markets form nearby. Settlements expand outward from its edges. A bridge is not only an engineering solution, it is an economic magnet. In early cities, rivers were both protection and obstacle. They defended against invasion, but interrupted trade. Whoever controlled the crossing controlled the flow of goods. Bridges therefore became strategic points, and with strategy came revenue. Many medieval bridges required payment to cross. These tolls were not arbitrary. They funded maintenance, repairs, and sometimes the construction itself. A bridge had to sustain not only physical load, but financial continuity. Toll systems varied by region and era. Merchants transporting livestock, textiles, grain, or salt often paid different rates depending on the type and volume of goods. Some bridges were funded by local rulers, others by merchant guilds or religious institutions. In certain cities, crossing a bridge meant passing through a gate where officials recorded movement and collected fees. The act of crossing became both physical and transactional. Because bridges gathered traffic, they also gathered opportunity. Traders preferred routes that guaranteed consistent passage. A stable bridge reduced the risk of delay caused by seasonal flooding or unreliable ferries. Over time, entire trade corridors formed around dependable crossings. Markets did not grow randomly. They clustered where routes converged, and bridges were natural points of convergence. In some cases, bridges evolved beyond simple passageways. Space above the river was valuable, especially in dense medieval cities where land within walls was limited. Instead of leaving the bridge as an open platform, builders constructed shops and dwellings directly on top of it. These structures generated rent and commercial activity, transforming the bridge into a street suspended over water. One of the most well-known examples is the Ponte Vecchio. Built in its current form in the 14th century, it spans the Arno River and supports a continuous row of shops along both sides. Originally occupied butchers and tanners, the shops were later reassigned to goldsmiths and jewelers, whose work produced less waste and odor. The bridge became not only a crossing, but a marketplace, a corridor of commerce elevated above the current. This arrangement reflects a deeper truth about urban space. In cities constrained by walls or geography, every square meter carries value. Building atop a bridge allowed economic activity to occupy what would otherwise be transitional ground. The structure below supported both pedestrians and storefronts, merging infrastructure with architecture. The bridge ceased to be merely connective. It became inhabited. Such bridges altered the experience of crossing. Instead of moving through open air with water visible on both sides, pedestrians passed through narrow lanes of shops and homes. The river became background rather than focus. Sound changed as well. The flow of water blended with conversation, bargaining, footsteps, and the rhythm of daily trade. A bridge with buildings felt less like a boundary and more like an extension of the city. Economically, these structures created layered income. Toll collection provided direct revenue. Shops produced rent and commerce. Increased traffic supported surrounding districts. A well-positioned bridge could elevate the prosperity of an entire neighborhood. Its value extended beyond transport into taxation, trade control, and urban planning. The placement of a bridge often determined the direction of expansion. When a new crossing opened, roads adjusted. Residential areas formed near the most convenient routes. Warehouses clustered where goods entered or exited the city. Over time, the bridge influenced not only movement, but spatial hierarchy. Streets aligned with it gained prominence. Others diminished. Even when toll systems eventually disappeared or were standardized under national infrastructure policies, the economic logic remained. Bridges reduce travel time. Reduced travel time lowers transportation cost. Lower cost increases trade volume. The relationship between structure and economy became embedded in planning decisions. Modern highways and freight corridors still follow this principle, though the toll booth may have become digital or symbolic. In the medieval world, however, the connection was visible and immediate. Coins exchanged hands at the entrance. Merchants paused mid-crossing to conduct business. Residents lived above flowing water, their livelihoods supported by the steady passage below. A bridge with buildings was not an anomaly, but a practical solution to density and demand. The presence of structures atop a bridge also signaled trust. A community would not build homes or shops on a structure it believed temporary. Investment implied confidence in stability. The bridge became part of the city's architectural fabric, as permanent as any plaza or cathedral. Its economic function and structural form intertwined. When we consider bridges inside civilization, we see that they do more than shorten distances. They reorganize activity. They concentrate movement. They generate revenue. In certain cases, they transform into streets in their own right, lined with commerce and life. A bridge like Ponte Vecchio demonstrates that crossing and commerce can occupy the same space, suspended together above the current. In this way, a bridge becomes more than an object of engineering. It becomes a platform for exchange, a line of connection that gathers stories, goods, and livelihoods. Water flows beneath, trade flows across, and the city quietly reshapes itself around the path in between. A bridge connects two sides, but in times of conflict, it becomes something else entirely. It becomes a target. Where there is a crossing, there is movement. Where there is movement, there is strategy. Armies have long understood that destroying a bridge can slow an advance, isolate a region, or fracture supply lines. In war, a bridge is no longer infrastructure. It is leverage. Throughout history, retreating forces have burned wooden bridges to delay pursuit. Stone arches have been mined and blasted to interrupt enemy passage. In more modern conflicts, aerial bombardment has focused deliberately on crossings over rivers and valleys. The logic is simple. Sever the bridge and you sever connection. Trade stops, reinforcements stall, communication narrows. Yet when a bridge falls, the damage extends beyond military advantage. A destroyed bridge divides communities that once moved freely. Families separated by a river may find themselves suddenly distant. Markets collapse, daily routines fracture. The physical gap returns, but now it carries memory. Some bridges become symbols precisely because of their destruction. The Mostar Bridge once arched gracefully over the Neretva River, linking two sides of a city shaped by layered cultures and histories. Built in the 16th century during the Ottoman period, its single stone arch became an architectural emblem of connection. In 1993, during the Bosnian War, the bridge was deliberately destroyed by artillery fire. The collapse was filmed, watched, and remembered. When the arch fell into the river, it was not only stone that shattered. The bridge had stood for centuries as a shared landmark. Its absence became a visible wound in the cityscape. The river still flowed, but the symbolic link between communities was broken. The destruction transformed a structure into a memory. Reconstruction after war is never simply technical. Engineers must determine whether to rebuild exactly as before or introduce modern modifications. Historical records, surviving fragments, and archaeological surveys guide the process. In the case of Masdar, original stones were recovered from the riverbed where possible. Traditional construction techniques were studied and replicated to maintain authenticity. Reconstruction techniques often balance historical fidelity with contemporary safety standards. Hidden reinforcements may be added to improve resilience while preserving external appearance. Materials are tested to ensure compatibility with surviving elements. The aim is not merely to replicate shape, but to restore continuity. Rebuilding a bridge can serve as an act of reconciliation. It signals an intention to reconnect what conflict divided. When Masdar's Bridge was reopened in 2004, it was not presented as a new structure, but as the continuation of an interrupted history. The restored arch mirrored the original form, its curve once again guiding pedestrians across the river. Cultural memory attaches itself to structures that endure long enough to gather stories. When those structures disappear, absence becomes part of collective identity. A bridge rebuilt in the same location carries both its past destruction and its present restoration. It stands as evidence that physical connection can be broken, but also repaired. The process of reconstruction is meticulous. Foundations are reassessed to ensure they remain stable after years of exposure. Stones are shaped to match historical dimensions. Mortar composition may be adjusted to replicate original texture while improving durability. Each decision balances respect for heritage with the realities of modern engineering. In many regions, international organizations assist in preserving or restoring historically significant bridges. Documentation, funding, and technical expertise converge to protect these crossings as cultural landmarks. The value of such bridges lies not only in utility, but in symbolism. They represent continuity across generations. Destruction changes how a bridge is perceived. A structure once taken for granted becomes charged with meaning. Its image appears in photographs, literature, and conversation. When rebuilt, it carries the weight of that memory. The crossing is no longer ordinary. It becomes ceremonial in a quiet way. Bridges destroyed in war remind us that infrastructure exists within political realities. Concrete and stone may be neutral materials, but the decision to build or demolish is never neutral. A crossing can embody cooperation, coexistence, or division, depending on the context in which it stands. Reconstruction does not erase loss, it acknowledges it. The restored structure stands not as denial of history, but as dialogue with it. Pedestrians crossing Masdar today walk over an arch that echoes its predecessor, aware that what seems permanent can be undone and remade. In this way, bridges participate in cycles of fracture and repair. They are built to connect, destroyed to divide, and rebuilt to heal. Each phase leaves a trace, not only in stone and mortar, but in the collective memory of the people who lived beside them. A bridge's physical life may follow the logic of engineering, yet its symbolic life follows the logic of history. Reconstruction introduces a different kind of force. It is deliberate and forward-looking, yet it cannot ignore what came before. Engineers measure spans and loads, but communities measure loss and continuity. When stone is lifted back into place, the act carries more than structural purpose. It signals that separation is not permanent and that repair is possible. Where water once flowed beneath a fallen arch, memory lingers in the space it left behind. When the curve rises again and the crossing reopens, the river reflects something altered. A restored bridge is never simply new. It carries the weight of interruption and the quiet decision to reconnect, reminding those who cross it that connection, once broken, can be chosen again. A bridge may be designed on paper as a set of loads and forces, but once it opens to the public, those forces begin to move. Cars accelerate and brake, trains pulse across rails, and pedestrians walk, pause, turn, gather, and cross in rhythms that no calculation can fully predict. The human body, light on its own, becomes powerful in numbers. Engineers distinguish between static load and dynamic load. A static load is constant and unmoving, like the weight of the bridge itself. A dynamic load changes over time. It moves, shifts, accelerates, stops. Human footsteps belong to this second category. A single person crossing a bridge may seem insignificant, but each step applies a small, repeated force. When multiplied by hundreds or thousands, that repetition matters. Walking is not random impact. It has rhythm. Each step produces a vertical impulse, a brief downward force that slightly flexes the structure beneath. Bridges are not rigid plates suspended in air. They are elastic systems designed to flex within safe limits. This flexibility protects them from cracking under stress, but it also means that motion can be felt. When a crowd gathers on a bridge, dynamic load becomes collective. If individuals walk at slightly different paces, their impacts tend to cancel each other out. But under certain conditions, people unconsciously synchronize. This phenomenon, known as the synchronized step effect, occurs when individuals adjust their pace in response to subtle movement beneath their feet. Instead of dispersing force randomly, the crowd begins to move in rhythm. Synchronization can amplify vibration. When repeated forces align with the natural frequency of a structure, oscillation increases. A bridge has its own preferred modes of vibration, shaped by length, stiffness, and mass. If pedestrian steps match those frequencies, motion grows rather than dissipates. The bridge begins to sway more noticeably, encouraging further synchronization in a feedback loop. This dynamic was dramatically illustrated when the Millennium Bridge opened in 2000. Designed as a sleek pedestrian crossing over the River Thames, the bridge initially appeared stable under normal conditions. Yet on its opening day, as large crowds gathered, a lateral swaying motion developed. The movement was not structurally dangerous, but it was unexpected and uncomfortable. The cause was not structural weakness in the conventional sense. It was pedestrian-induced lateral vibration. As the bridge began to sway slightly, walkers adjusted their steps to maintain balance. Their synchronized motion increased the lateral force, which in turn amplified the sway. This effect had not been fully anticipated in the original design calculations, which focused primarily on vertical loads. Engineers temporarily closed the bridge to study the phenomenon. Detailed analysis revealed that even modest lateral movement could encourage synchronization among pedestrians. The solution involved installing dampers, devices designed to absorb and dissipate vibrational energy. These dampers reduced oscillation by converting movement into heat, allowing the structure to return to equilibrium more quickly. The Millennium Bridge case changed how engineers approach pedestrian bridges worldwide. Human behavior became an explicit design consideration. Models now account for possible synchronization effects and lateral forces induced by crowds. The bridge itself did not fail. Rather, it revealed that structural dynamics extend beyond material strength into collective human response. Pedestrian-induced vibration is now recognized as a distinct design category. Engineers measure expected walking frequencies, typically around 2 steps per second, and compare them with the natural frequencies of the structure. If these frequencies align too closely, adjustments are made to stiffness or damping to reduce the likelihood of resonance. The goal is not to eliminate motion entirely, but to keep it within comfortable and controlled limits. Movement is intrinsic to bridges. Even large highway spans flex under passing vehicles. Thermal expansion causes decks to lengthen and contract daily. What distinguishes pedestrian bridges is the sensitivity of the human body to motion. People feel sway more acutely than vehicles do. Perception becomes part of performance. Crowd weight is also variable. A single person might weigh 70 kilograms, but a densely packed group can produce significant distributed load. Public events, celebrations, or protests can concentrate hundreds of people in a confined area. Engineers designed for maximum expected occupancy, ensuring that both static and dynamic components remain within safe thresholds. The interaction between structure and human rhythm introduces subtle complexity. A bridge does not merely support people, it responds to them. As footsteps fall, the deck deflects slightly. As it deflects, walkers adjust instinctively. The system becomes interactive. In most cases, the exchange remains imperceptible. In rare instances, it becomes visible. Design strategies to manage dynamic load include increasing stiffness, adding tuned mass dampers, or altering cable tension in certain systems. Tuned mass dampers consist of secondary masses attached to the structure that move out of phase with the primary motion, counteracting vibration. These systems are carefully calibrated to match specific frequencies, reducing amplitude during peak movement. The study of dynamic load highlights a broader truth about bridges. They are not static monuments. They are responsive systems. The forces they experience are not only environmental or mechanical, but human. The cadence of footsteps, the distribution of weight, and the subtle coordination of movement all influence structural behavior. Crossing a bridge is often described as a simple act, a movement from one bank to another. Yet beneath that simplicity lies a conversation between rhythm and resistance. Each step contributes a fraction of force. Each fraction interacts with the bridge's geometry and material properties. When those forces align, motion emerges. The lesson of pedestrian vibration is not fragility, but sensitivity. A bridge strong enough to carry thousands of people can still respond perceptibly to their collective rhythm. Strength ensures safety. Control ensures comfort. Together, they shape the experience of crossing. A bridge does not merely carry weight, it absorbs motion. It accepts the pulse of footsteps and translates it into controlled movement. The structure stands firm, yet never completely still, reminding us that stability is not the absence of motion, but the careful management of it. Most bridges ask us to trust what we cannot see. Steel is hidden inside concrete. Cables are tensioned beyond visibility. Foundations disappear beneath water or soil. Glass bridges reverse that relationship. They remove visual certainty. The structure may be stronger than ever, yet it feels less secure because the ground beneath our feet becomes transparent. Glass as a structural material carries a psychological burden that steel does not. When we look at steel, we assume strength. When we look at glass, we think of fragility. This association persists even when the glass is engineered to withstand loads far greater than those of traditional flooring. Perception does not always follow calculation. Modern bridge glass is not ordinary window glass. It is typically laminated and tempered, composed of multiple layers bonded together. Tempering increases strength by introducing internal compressive stress. Laminating ensures that if one layer cracks, the others maintain integrity. The result is a panel capable of supporting significant weight while remaining transparent. Structurally, it is designed with redundancy. Psychologically, it feels exposed. The introduction of transparent floors alters how people walk. When the surface beneath becomes visually open, movement slows. Steps become tentative. The body lowers its center of gravity slightly, adjusting instinctively. Even when individuals know the structure is safe, their balance system reacts to visual depth. Height intensifies this reaction. Looking down from a significant elevation triggers a physiological response. Heart rate may increase, muscles tighten. This is not irrational fear, but an evolutionary mechanism. The human brain evolved to treat height as potential danger. Visual cues of depth activate caution before conscious reasoning intervenes. Transparent bridges amplify that depth cue. Instead of a solid deck blocking the view below, the eye receives uninterrupted information about distance. The body responds as if the barrier were absent, even when it is present. The sensation is not simply fear. It is cognitive dissonance between what the eyes perceive and what the feet feel. The Zhangjiajie Glass Bridge exemplifies this shift in experience. Suspended high above a canyon in China's Zhangjiajie National Forest Park, the bridge features a glass deck spanning hundreds of meters. Visitors walk across panels that reveal the landscape far below, transforming crossing into an encounter with vertical space. Structurally, the bridge is designed with substantial safety margins. The glass panels are layered, tested under load, and supported by a steel framework beneath. Demonstrations during its opening included controlled impact tests to show resistance to cracking. The engineering was deliberate. The fear response, however, remained authentic. What changes on a glass bridge is not the load applied to the structure, but the load applied to the mind. Psychological weight replaces physical uncertainty. Individuals who move confidently across opaque surfaces may hesitate mid-span. Some crouch, others grip railings tightly. The body interprets transparency as vulnerability. Interestingly, crowd behavior shifts as well. In groups, hesitation can spread visually. One person slowing down prompts another to adjust. Laughter, nervous comments, and pauses ripple through the crossing. The structure remains stable, but the human rhythm becomes irregular. The bridge influences behavior not through vibration, but through perception. Glass bridges reveal how much of structural experience depends on expectation. On a steel or concrete deck, users rarely consider the thickness beneath them. Trust is assumed. On a transparent floor, thickness is visible yet psychologically insufficient. Even when panels are several centimeters thick, the visual clarity creates an illusion of thinness. Designers of glass bridges account for this dual reality. Structural calculations determine panel size, load capacity, and support spacing. Simultaneously, experienced design considers railing height, framing visibility, and visual contrast. Subtle cues can reassure users without reducing transparency. Frosted patterns, slight tinting, or visible steel ribs provide reference points for balance. The psychology of height intersects with spectacle. Glass bridges often attract visitors precisely because they provoke controlled discomfort. The crossing becomes an event rather than routine passage. Photographs capture not only scenery but emotional reaction. The bridge functions as both infrastructure and destination. From a structural perspective, glass panels must resist concentrated loads from footsteps, environmental loads such as wind and potential impact. Redundancy is critical. If one layer fails, others must continue to perform. Maintenance protocols include regular inspection for microcracks or surface damage. Transparency demands vigilance. The presence of glass also alters the relationship between user and landscape. Instead of walking above a concealed river or valley, individuals engage directly with the space below. The bridge becomes a frame for viewing depth. Transparency turns crossing into observation. Fear on a glass bridge is rarely about collapse. It is about exposure. The absence of visual obstruction creates a sensation of suspension. The body senses height without the comforting illusion of solidity. Yet that same sensation generates awe. The view is uninterrupted, expansive, immediate. Bridges have always managed physical forces. Glass bridges manage perception. They demonstrate that safety is not only a matter of strength, but of experience. The structure may be engineered to exceed required standards, yet the human response remains layered and complex. A glass bridge stands as proof that weight is not only measured in kilograms or tons. There is also psychological weight, carried in the chest and shoulders, felt in cautious steps and tightened hands. The structure holds steady. The mind negotiates the rest. If we step back from individual spans and look at the planet as a whole, the scale changes dramatically. In the ancient world, only a few hundred bridges have survived to the present day. Today, The number is no longer counted in hundreds or even thousands, but in millions. The bridge is no longer a rare achievement. It is a global network. In the United States alone, more than 620,000 bridges are officially recorded in national databases. Each one has an identification number, inspection history, structural classification, and condition rating. Some carry highways across rivers. Others are small rural crossings over narrow streams. Together, they form an immense catalog of connection. Globally, precise numbers are difficult to confirm because definitions vary. Some countries count only major highway bridges. Others include smaller culverts and pedestrian spans. Even with conservative estimates, engineers suggest that there are likely between 3 and 4 million bridges worldwide. The difference between a few hundred surviving ancient structures and millions of modern crossings reveals how infrastructure has become continuous rather than exceptional. With that scale comes responsibility. A bridge built centuries ago required local maintenance. A bridge built today becomes part of a vast system. Inspecting millions of structures manually at frequent intervals is costly and time-intensive. As infrastructure ages, the challenge shifts from construction to monitoring. Structural health monitoring has emerged as a response to this complexity. Structural health monitoring refers to the continuous or periodic observation of a bridge's condition using sensors and data analysis. Instead of relying solely on visual inspections every few years, engineers can track performance in real time. Strain, temperature, vibration, and displacement become measurable variables. Fiber optic sensors play a central role in many modern monitoring systems. These sensors use light transmitted through thin glass fibers to detect changes in strain or temperature. When the fiber stretches or compresses, the properties of the light signal change slightly. These changes can be measured with high precision over long distances. Because fiber optics are resistant to electromagnetic interference and corrosion, they are well suited for harsh structural environments. By embedding sensors directly within concrete or attaching them to steel members, engineers gain continuous insight into how a bridge behaves under traffic and environmental loads. Patterns emerge over time. Small deviations from expected behavior can signal early signs of fatigue, cracking, or foundation movement. Maintenance becomes predictive rather than reactive. Digital twin technology extends this concept further. A digital twin is a virtual model of a physical structure that mirrors its real-time condition. Data collected from sensors feeds into a computational model, updating simulations continuously. Engineers can test scenarios within the digital twin without affecting the physical bridge. They can simulate increased traffic loads, extreme wind events, or long-term material degradation. The advantage of a digital twin lies in anticipation. Instead of waiting for visible damage, engineers can evaluate trends. If strain in a particular member gradually increases beyond expected levels, investigation can begin before failure risk rises. The bridge becomes not just an object, but a monitored system with a digital counterpart. Scale remains the defining factor. Monitoring one historic stone arch required occasional inspection. Monitoring millions of modern bridges requires data infrastructure. National agencies maintain centralized databases. Inspection reports are digitized. Condition ratings influence funding decisions. Infrastructure management becomes an exercise in information as much as engineering. The contrast between ancient and modern numbers sharpens perspective. From a few hundred surviving stone bridges across millennia to millions of reinforced and steel spans in active service, the human relationship with crossing has expanded exponentially. The bridge is no longer a singular achievement in a landscape. It is embedded in daily life, often unnoticed. Yet scale does not eliminate vulnerability. The larger the network, the more critical its reliability. A single bridge closure in a dense transportation corridor can disrupt supply chains and commuter patterns. Monitoring systems aim to reduce unexpected failures by increasing awareness. Data becomes a structural element in its own right. The modern bridge exists in two forms simultaneously. There is the physical structure of steel, concrete, and cable. And there is the digital layer of sensors, models, and inspection records. Together, they create a feedback loop between performance and prediction. Information flows alongside traffic. In a world with millions of bridges, individual crossings may seem ordinary, but each one carries weight, movement, and expectation. Structural health monitoring does not make bridges invincible. It makes them observable. It transforms maintenance from guesswork into analysis. From a handful of ancient arches that survived by geometry and chance to a global inventory of millions tracked by sensors and algorithms, the evolution is striking. The bridge has moved from isolated monument to monitored network. And in that shift, the challenge has changed. Building is no longer enough. Watching, measuring, and understanding have become equally essential. This expansion of awareness also reshapes how governments prioritize infrastructure. With hundreds of thousands of bridges in a single country and millions worldwide, resources must be directed where risk is highest. Data allows engineers to rank urgency, comparing structural condition, traffic volume, and strategic importance. A rural crossing with light traffic demands a different response than a major urban artery, carrying thousands of vehicles per hour. Digital records accumulate over decades. Each inspection adds another layer to a bridge's history: corrosion levels, crack measurements, bearing condition, load ratings. Over time, patterns emerge. A slight increase in deflection under similar loads may signal material fatigue. A gradual shift in vibration frequency could indicate stiffness loss. What once required intuition now benefits from measurable trend analysis. Climate data increasingly integrates with monitoring systems as well. Rising temperatures, heavier rainfall, and freeze-thaw cycles influence structural performance. By correlating sensor readings with environmental conditions, engineers can better understand how weather accelerates wear. Infrastructure management becomes interdisciplinary, linking structural mechanics with meteorology and materials science. The scale difference between ancient and modern infrastructure also alters public perception. In earlier centuries, a single bridge might define a region. Today, commuters cross multiple bridges in a single day without noticing. Their invisibility is a sign of success. Bridges that function quietly fade into the background of daily life, yet their reliability depends on constant attention behind the scenes. Monitoring does not eliminate the need for human inspection. Engineers still walk beneath decks, examine joints, and evaluate surfaces directly. Technology complements rather than replaces judgment. Sensors can detect anomalies, but interpretation requires expertise. Data without understanding remains incomplete. As bridge networks expand, resilience depends not only on strength, but on coordination. Alternative routes, distributed traffic patterns, and continuous monitoring reduce vulnerability when one structure requires repair. Modern bridges exist within an ecosystem of data, cataloged, measured, inspected, and digitally modeled rather than simply assumed to be sound. What once relied on geometry and endurance now relies on information as well, with sensors and digital twins quietly extending the life of structures that millions cross each day. Bridges have always responded to gravity, water, and wind. In the coming decades, they will respond to something more gradual yet equally powerful: climate shift. The environmental conditions under which many bridges were originally designed are no longer stable assumptions. Temperature ranges widen, storm intensity increases, coastlines slowly redraw themselves. The bridge, once built for a predictable century, must now anticipate change. Sea level rise presents one of the most direct challenges. Coastal bridges and low-lying approach roads face higher baseline water levels and more frequent flooding events. A structure designed decades ago for rare storm surges may now encounter those conditions regularly. Foundations, bearings, and drainage systems must adapt to prolonged exposure to saltwater and fluctuating tides. Salt accelerates corrosion, especially in steel reinforcement hidden within concrete. Rising temperatures influence material behavior as well. Thermal expansion becomes more pronounced when seasonal extremes grow wider. Expansion joints, bearings, and support systems must accommodate greater movement without transferring excessive stress into the structure. What was once a manageable range of contraction and expansion may stretch beyond earlier design assumptions. Wind patterns are also shifting. In some regions, storm systems intensify, producing stronger gusts and more dynamic loading. Bridges with long spans or high towers are particularly sensitive to these forces. Design codes evolve to incorporate updated wind maps and probabilistic models. Engineers must ask not only how a bridge performs today, but how it might perform under future conditions not yet fully measured. Sustainability enters the conversation alongside resilience. Traditional concrete production generates significant carbon emissions due to cement manufacturing. Steel production also carries environmental cost. Reducing the carbon footprint of infrastructure has become a priority in many countries. Alternatives include supplementary cementitious materials, recycled steel content, and innovative mixed designs that reduce cement demand while maintaining strength. Designing for longevity becomes a climate strategy in itself. A bridge with a 100-year design life spreads its environmental cost over a longer period. Durability reduces the need for replacement, reconstruction, and additional resource extraction. Protective coatings, corrosion-resistant reinforcement, and improved drainage systems all contribute to extended service life. Yet longevity depends on maintenance. Many countries face aging infrastructure, bridges built in the mid-20th century now approaching or exceeding their intended lifespan. Fatigue accumulates, bearings wear, protective systems deteriorate. Inspection regimes grow more complex as networks expand. Maintenance is less visible than new construction, but it is equally critical to safety. In the United States, the American Society of Civil Engineers regularly evaluates the condition of national infrastructure. Their reports often highlight the gap between funding needs and maintenance realities. Bridges are graded not only on structural adequacy, but on long-term performance and resilience. The conversation shifts from building new icons to preserving existing systems. Digital monitoring technologies are increasingly integrated into modern bridges. Sensors embedded within structures track strain, temperature, vibration, and corrosion indicators in real time. This data allows engineers to identify deterioration before it becomes visible. Preventive maintenance replaces reactive repair. A bridge becomes a monitored system rather than a static object. Adaptation also includes reconsidering location and elevation. In some coastal regions, new bridges are built higher to anticipate future sea levels. In others, protective barriers or redesigned drainage systems mitigate flood risk. Climate resilience becomes part of initial design rather than an afterthought. Carbon reduction, resilience, and longevity intersect in material innovation. Researchers explore low-carbon concrete alternatives, high-performance steels with longer fatigue life, and composite materials resistant to corrosion. The goal is not only to build stronger bridges, but smarter one structures that anticipate environmental stress rather than simply endure it. The next era of bridge design is less about breaking records of length or height and more about managing uncertainty. Environmental models provide projections, not certainties. Engineers must design with margins that account for variability. Flexibility, once primarily a structural trait, becomes a planning philosophy. Across centuries, bridges have evolved from stone arches to steel spans, from timber crossings to glass decks suspended above canyons. They have carried trade, survived conflict, absorbed vibration, and adapted to new materials. As we look forward, the essential purpose remains unchanged: to create passage where there was once separation. The forces surrounding them may shift, but the intention endures. A bridge is a promise extended across space, and with careful design, that promise can continue into the next century and beyond.